Now we need to start studying discrete and continuous random variables in order to calculate probabilities. And this is a topic actually we're going to be using for a large part of the remainder of the semester. So a couple of definitions first. First, random variable. What is a random variable? A random variable, typically represented by, say, x, has a single numerical value determined by chance for each outcome of the procedure. Okay? So, again, a single numerical value determined by chance, okay, for each outcome of the procedure. So, probability will be involved here. Probability distribution is a graph, a table, or a formula that gives the probability for each value of the random variable. And so, the idea here is that if we have these outcomes of a procedure, and we want to calculate the probability of each one and represent that somehow, that's what a probability distribution will do. The two primary ways we'll look at it will be with a graph and a table, and which one we use really depends on which type of random variable we have. So let's look at discrete random variable. Discrete random variable has either a finite number of values or a countable number of values, where, this idea of countable refers to the fact that there might be infinitely many values, but they're able to come about by counting. Usually, the best way to describe this discrete random variable would be if you could count up the values with one of those clickers they use to count people coming through a door at a concert or something. And if you could count the number of values that way, then you would have a discrete random variable. And the key word here is it's finite or countable. And if it's finite or countable, we could list the outcomes somehow. And if we can list the outcomes somehow, again, along with their probabilities, because that's what a probability distribution does, it lists the outcomes, okay, from the random variable, as along with their probabilities. We could use a table to do this. That's largely because of that finite countable concept with the discrete random variable. Then we have continuous random variable, and it's basically kind of the opposite here. It says infinitely many values. And those associated with them could be measurements on a continuous scale. There's no gaps or interruptions in that scale. And because there's infinitely many of them, you can't count them all up. It's usually measured on a scale, so like weights, time, these would all be continuous random variables. These are all measured in scales. So in which case, a table is not going to work very well because it'd be very hard to list every single outcome. Again, because there's infinitely many, right? It's not countable. And so to put it in a table would be impossible. So instead, with the continuous random variable, we use a graph. So let's look at some examples. Let's start with discrete. Okay. So we have a discrete probability distribution, okay, for a discrete random variable. We would make a table and list the outcomes, okay, for our random variable in the first column, and the probability of each one of those outcomes is labeled in the second column. And this table works out very nicely to help us see the probabilities for a given situation, but only in a discrete random variable. Okay? Again, because it's a finite or countable amount of outcomes, we can just list them here in the table. There are two things that a discrete probability distribution would really need. One is that each probability has to be between 0 and 1, which is basically just it has to follow the rules of probabilities themselves. Every probability we've calculated up to this point, we've said, has to always be between 0 and 1. 0 means it will never happen, and 1 means it's always going to happen, and then everything in between. So that's one of them. Two, the sum of all the probabilities has to equal 1. So if we add up this column right here, those all have to add up to be 1. So we need those two things for a probability distribution. And mainly because they represent all the outcomes, which means one of them is definitely going to happen if they're all the outcomes. Therefore, the probability that any one of those things will happen should be the highest probability one. So here's an example that we're working with this table. So this table represents a hospital researcher who's interested in the number of times the average post-op patient will ring a nurse bell, okay, in a 12-hour shift. So the random sample was for 50 patients, and we got a bunch of information there. And so we're going to let X, which is our random variable here, represent the number of times a patient rings a bell in a 12-hour shift. So for this, we're just going to say it was between 0 and 5 times. That's definitely a countable amount, right? A finite countable amount. 0, 1, 2, 3, 4, 5. That's our random variable. So this is a discrete random variable. And the probability of each one of those, P of X, represents the probability that each one of those things is going to happen. And so you don't have to calculate the probability. It was done here for you. This would not be a very easy probability to calculate anyway. You would need the data to be able to do that and calculate how many times each one occurred. So basically what they did is they said, all right, well, here, out of the 50 patients that they surveyed, 4 out of the 50 rang at 0 times, 8 out of the 50 rang at 1 time. And so they listed the probabilities here. In total, you should get the whole set of 50. Okay, if we add it all up, we should get 50. So is this a probability distribution function? Well, are all those probabilities between 0 and 1? Sure. Do they all add up to give you 1? Well, yeah, 4 plus 8 is 12. 12 and 16 is 28. 28 and 14, I'm just adding the numerators here. 28 and 14 would give you 42. 42 and 6, and then another 2 again would give you 50, so 50 over 50 is 1. So yes, this is a probability distribution, but we can then use this table to answer other questions. If I said, what's the probability that someone rang the bell less than 2 times? Well, the probability that it rang the bell less than 2 times means 0 times or 1 time. And so these are the total number of people who rang it less than 2 times, and the probabilities would be added together, and therefore your probability in that situation would be 12 out of 50. So we can use this table to do a lot, and it's really nice to have a probability distribution in front of you when you're working with a given discrete random variable. But again, this only works for discrete random variables because there's a finite or countable number of outcomes that we can list in the table nicely, along with their associated probabilities. Then we talk about something called an expected value, which is a lot of what we really just did. An expected value, often referred to as the long-term average or mean. So it's basically what we could think of as the mean from a probability distribution. So, over a long term, if you were going to perform the experiment over and over and over and over again, what would you expect the average outcome to be? Okay, the average value. And so that's the expected value. We could use the law of large numbers to do this, and that would really help us in calculating the expected value. But we could do it a little bit quicker. So first off, the law of large numbers. The law of large numbers says that as the number of trials in a probability experiment increases, the difference between the theoretical probability of an event and the relative frequency should approach 0. What that means is that your actual probability and your frequency probability will become one and the same. Think about flipping a coin. If I flip the coin, before I even flip it, I know that the probability of a heads is going to be 1/2. Okay? I can calculate that. That's my theoretical probability. I can calculate that before I even get started. Or I can flip the coin 10 times and record how many heads I got, which should be pretty close to 5 heads out of 10, but maybe not exactly 5. Maybe it's 6 heads out of 10. And then I can flip it 10,000 times. Then I can flip it 1,000,000 times. And the more times I do it, the closer I'll get to that probability of 1/2 that I know is the theoretical probability. So if I flip the coin 1,000,000 times, I should get really, really close to 500,000 heads. So the more times I do something, the closer I get to the actual probability. So we can use this idea along with the concept of expected value. What expected value does is it doesn't make us do things over and over and over again. Okay. So the problem with that law of large numbers is you have to perform a trial over and over. I have to flip a coin a million times. But if I could calculate the expected value of a given situation, what should happen in the long term, I could use that to my advantage. Calculating expected value from a probability distribution when we have a discrete random variable is really easy, okay? In order to find the expected value, we use the mean symbol to do that, the mean of the population symbol to do that, because remember, this is like the average value you would get in the long-term average. So all we have to do is simply multiply each value of the random variable by its probability, and then add all that up. So random variable times probability, random variable times probability, and then add all those up, we get our answer. So here's an example. Men's soccer team plays soccer 0, 1, or 2 days a week. All right, so those are your outcomes. They are discrete because they are countable, finite number of outcomes. Okay. The probability that they play 0 days was found to be 0.2. The probability they play 1 day is 0.5. The probability they play 2 days is 0.3. So we got this here, 0, 1, and 2. And these are the probabilities for each one of those. So find the long-term average or expected value of the number of days per week men's soccer team will end up playing. So if you were to look at this over the course of 10 years, rather than sit there and record how many times they played 0, 1, or 2 times and then actually find the average, what we could say is, let's figure out what the long-term average should be, what we should expect that average to be based off of these probabilities. Okay? So we would multiply this times this, the variable times its probability, and we get 0. 1 times its probability, we get 0.5. 2 times its probability, we get 0.6. And then if we add those together, the sum of all those would give me 1.1. So what we could say here is that the expected value is 1.1. So that would mean that on average, if you were to look at this over the course of years and years and years, the average number of days that this soccer team would most likely play per week would be 1.1 days. And the nice thing about this is I don't have to look at 10 years worth of data to find what this expected mean or this expected value would be. And we're using probabilities to predict that. Let's do it with cards. Playing a game of chance, and you have 4 cards in a standard deck of cards. You want to guess the suit of each card before it's drawn. Okay? We're going to replace the cards in the deck. That's important because that's going to affect our probability. So the cards are replaced. You pay $1 to play this game. Right? If you guess the right suit every time, you get your money back. And $256. So basically you're up $256. If you lose your dollar. Okay? So if you're going to play this game over and over and over and over again, okay, what do you expect your profit to be when playing this game over a long term? Okay, what would that expected value be if you played for a long time? Well, let's think about it. Let's let X be our random variable, and that'll be the amount of money that you profit, okay? Not the outcomes, you win or lose, but let's make it monetary. Let's make it so that it's quantitative. So the amount of money you would win or lose, okay? So your profit would be negative $1 if you lose and $256 if you win. Okay, what's the probability that you actually guess this right 4 times in a row? Well, think about it. There's 4 suits total. So each time you pull a card out, the chance that you're going to guess it right would be 1 in 4. So the probability that the second card is guessed right is also 1 in 4. The third card is 1 in 4. The fourth card is 1 in 4. The probability that all of them were 1 in 4. So this one's correct, this one's correct, this one's correct, and this one's correct. You would multiply those probabilities together using the multiplication rule. And what you get is 1 over 256. So this is the probability that you're going to get this all correct. Okay? 4 cards drawn from a deck of cards. You guess the right suit every single time, 4 times in a row. So now let's construct a probability distribution for this discrete random variable. So our outcomes are we lose $1, so minus $1, or we gain $256. We know the probability that we're going to be right is 0.0039. That's the probability that we're going to actually win $256. The probability that we're going to lose would basically be the probability that we mess up. Well, that should be the opposite of winning, and we know the total probabilities have to equal 1, so if there's only one other outcome, this other outcome is pretty easy to find the probability for. If we do 1 minus 0.0039, okay, we could figure out that the opposite probability would be 0.9961. All right, so now we have our table set up. 2 outcomes, each one with its own probability. Basically, the top probability is a complement of the bottom probability. So now let's calculate the average or the expected value long term. My chances of winning are not very good. But if I win 1 out of 256 times, I would break even, right? So the question is, all right, well, what's your chance of winning or losing in the long term? So if we multiply this times this, and this times this, and then add those together. So 0.0039 times 256, 0.9961 times -1, then add those together. Okay. What we end up with is 0.0023. Or if you really want to look at this, we could say it's 23 cents. That's in terms of dollars. Remember, this is in dollars. So if you think about it in dollars, it's the same thing as 23 cents. Okay. So in the long term, if you were to play this for a long time, you're expected to win 23 cents. Which actually isn't bad, considering you're expected to be ahead. This is a game that you would expect in the long term to make some money on. 23 cents, but some money. If you played this whole thing out with any game in, say, the casino, any of the games that are in the casino, and you created your probability distribution based off of the odds and the probability of winning and losing, you're going to come out negative nearly every single time. It's always weighted in terms of the casino's favor. But in this game, the way this game was set up, just picking 4 cards out of the deck of cards and guessing it 4 times in a row, you have a pretty good shot of being up. It says in the long term, you should expect to be up 23 cents. Not bad. Now we need to study continuous random variable a little bit closer. And this is something we're going to spend a lot of time on. It's a lot more complicated. We're going to do it in different ways depending on what the probability function looks like. The biggest issue with the continuous probability function is that there are infinitely many outcomes on a sliding scale. And so a table just doesn't work, and we have to do these by a graph, and that's where the function is going to come in. So if we look at the graph of a continuous probability function, it's going to be a curve, okay? And we'll look at the area bounded by this curve to help us find probability. So probability will be represented by the area under the curve. The curve's called the probability density function, or PDF, not the same PDF you use as a file, but probability density function. That's the curve. We're going to look at a couple of common curves. We're not going to look at just random ones because the common ones will be more helpful. A couple of things that we need for a probability, continuous probability distribution is the outcomes are measured. They're not counted, right? It's not countable. It's infinite. So typically they're measured: time, weight, heights. These would be things that we would measure and therefore would be in the continuous probability distribution. The entire area under the curve, okay, has to be equal to 1. This is similar to the sum of all the probabilities in the discrete random variable have to equal 1 because the area under the curve represents all the probabilities. So the total area has to equal 1. You've got to keep that in mind. It's going to be very important. Probability is found for intervals of x values, not specific values. Okay, so in the table, we found the probability for very specific instances. This will be for a range or interval of values. So if we represent the probability that x is between c and d, okay? So x is greater than c but less than d. This represents the probability that our random variable is between c and d, okay? And then we'll calculate the area under the curve between c and d, okay? This and this are the same, whether I use the or equal to or not. It's going to be the same thing, again, because we're not going to be calculating what happens at a value. You know, in inequality, the not having the or equal to means you don't include these endpoints. But in a probability distribution that's continuous, whether we have the or equal to or not, it's going to represent the same probability we're trying to calculate. So again, when we define this continuous probability distribution function, we're going to use function notation to do that, okay? And you may not be familiar with function notation, so I'm not going to get too far into that. You know, usually we'd start talking about function notation in an intermediate algebra course, and then up from there, pre-calculus, calculus, etc. None of that is a prerequisite for this course, so we're not going to do too much function notation, but we define it as a function, and this f of x typically is the notation we would use for that. And again, probability and area are going to be equal to each other. So it's very important to understand that concept of calculating area is going to be the same thing as calculating probability. So here are three fairly common distributions of a continuous random variable. We have the uniform distribution, where the curve is a straight line all the way across, and it will create this rectangle. The nice thing about the uniform distribution is if we're trying to use area and probability to represent each other, it's very easy to calculate areas of a rectangle. The downfall of the uniform distribution is it just doesn't come up in real life a whole lot, okay? But nonetheless, if I was going to say, okay, I have a uniform distribution here, I want to find the probability that my random variable falls between 3 and 6. Here's 3, here's 6. If I can calculate this area, I could find the probability that I'm looking for. Another one would be a normal distribution. A normal distribution is the bell curve. This is going to be much harder to calculate area. Calculating areas under curves is a major topic in calculus. Well, we don't know calculus necessarily coming into this class. Some of you may have had it. A lot of you haven't. We're going to use calculus to get the answer, but we're not going to do any calculus to get it. We're going to use a table of values where the calculus has already been done for us. But anyway, if I had this picture set up and I had a normal distribution and I want to find the probability that my random variable falls between 1 and 2, and I could draw the picture, it would look like this. And if I could find this area, that would be the answer for the probability I'm looking for. And then there's the exponential distribution. Exponential distribution has this shape to it. This is a decreasing exponential, which is the typical one you would see here for this. And this type of curve where it decreases in this fashion, okay, would be our exponential distribution. These also, it's a curve, and finding area inside this curve is really calculus related, but we can find that area with a fairly simple formula because of the shape of the curve, whereas the bell curve is a lot more complicated. So anyway, if we had a exponential distribution, and I want to find the probability that my random variable fell between 2 and 4, I could draw this picture of an exponential distribution, say here's 2 to 4, this is what I'm looking for. And again, if I could find that area, I could calculate the probability I'm looking for. So these are the three major ones. This lesson we spend time on uniform and exponential, and I just briefly touch on normal. Normal is going to take a little bit longer. Next week's lesson will be more normal distribution problems. So let's look at uniform distribution. A continuous random variable has a uniform distribution if the values are spread evenly over a range of possibilities. And so that would give us this straight across. They're evenly distributed, the same all the way through, okay? And again, the graph would just be a rectangular shape. So here's an example. During certain time periods at JFK Airport in New York City, passengers arriving at a security checkpoint have waiting times uniformly distributed between 0 and 5 minutes. So they start at 0 minutes and they go to 5 minutes, and they're uniformly distributed. So the second I know that, I can draw my rectangle I know the start of the rectangle is at 0 and the end of the rectangle is at 5. So I can calculate that this distance right here is 5. Well, if I know that this has to be a probability distribution and the total area under this curve has to equal 1, then I can calculate the height of the rectangle from everything I know. So the height of the rectangle would have to be 0.2, because if I multiply 0.2 times 5, I get 1. All right? So I can figure out what the height is based off of the range of my outcomes. Okay? So let's say, given this situation, find the probability that a randomly selected passenger has to wait at least 2 minutes. So at least 2 minutes means 2 minutes or more. So I want to find the probability that my random variable is greater than or equal to 2. So here's 2. These would all be the people who waited 2 or more. So if I can calculate that area, I can find the probability I'm looking for. Well, this distance here, this side of the rectangle is between 2 and 5, so that's 3. The height, since it's uniform, is always 0.2 in this particular problem. So if I want to find this area, and it's a rectangle, it's simply length times width. So it would be 3 times 0.2, and I would get 0.6. So the probability that a randomly selected passenger has to wait at least 2 minutes, which is 2 minutes or more, would be 0.6. It's pretty simple to find the answer for this probability, considering we're just finding areas of rectangles. And that's the nice thing about a uniform distribution. Oftentimes you have to figure out what the height is based off of the total width, but that should be easy because you know the total area has to equal 1. And once you draw the picture, you just got to shade in what question you're looking for. Is x bigger than 2? Is x less than 2? Is x between two values? And then just do length times width, and you get your answer. Right? This is the nice piece about probability distributions. It's not always that easy because we're not always dealing with a uniform distribution, but this is the start. So then we have exponential distribution. Takes another step up. So whenever we use exponential distribution, we're often, concerned about time until something happens. That's usually when you would use an exponential distribution, and time would decrease. So that's why you have this sort of decreasing shape. So an example that it can be used with an exponential distribution will be the amount of time until an earthquake occurs. Okay, so you're waiting for an earthquake to occur in some region of the world. You can draw an exponential distribution to represent that. And so if I had an exponential distribution and I want to find this probability, I could do that. Now we need a formula to calculate that area. It's not a rectangle, right? So I can't just do length here, which would be 2 times height, because the height's different everywhere around here. So this isn't a rectangle, so we would have to come up with a formula for calculating that area. Again, really, it's largely based off of calculus. I mean, we're going to be doing calculus without doing calculus, essentially. That's the basis for what we're doing here. So if we use a couple of formulas to get to where we need to be. First off, exponential distribution, the notation we typically use is something like this. This means a random variable is approximated by an exponential distribution on m. The function that will give us the shape that we're looking for, that exponential shape that goes like that, is this function. Okay? Again, not necessarily needing a whole lot of information about functions to do this. The m in this is calculated by doing 1 over the mean. Okay? And in these exponential distributions, the mean and the standard deviation are equal to each other. This formula has this letter E in the formula, so m can be calculated using this formula, but E, okay, E is actually what we call the natural exponential. It's a number, okay? It's this number that's roughly 2.71828182846. It keeps going on forever. It never repeats itself. So it's this irrational number. It's a decimal that goes on forever, never repeats itself. You may not have studied E a whole lot. In your calculator, you would have the E to the X key in your calculator, which would allow you to calculate E to the first, E to the second, etc. Okay? The big thing you need from this is how we're going to calculate that area under the curve. And this cumulative distribution function will help us find that area. So if we want to find the probability that x is less than some other x, okay, we want to find a probability of something like this, this is what we're going to use, okay? But this formula will only give us less than, so gives us area to the left, okay? So if I said, okay, I want to find the area to the left of some value, I could use this formula to help me find that area, as long as I know m. E is just a number, we already know what that is. M would be the variable we need from the situation. That can always be found by knowing the mean. And then x is based off of what probability we're trying to find. So let's look at an example. So here, let's let x be the amount of time in minutes a postal clerk spends with his or her customer. Okay? The time is known to have an exponential distribution. That's a key word right there, exponential distribution. The second you hear that, as opposed to uniform distribution, we can think about drawing a curve that looks like this. And then they tell you the average amount of time is 4 minutes that someone would wait. The average amount of time. So our mean would be 4 minutes. So we have a continuous random variable because we're talking about time being measured on a scale, okay? Our mean is 4, so we would have to first calculate m. Once we calculate m, which is 1 over the mean, which would be 1/4, okay, we're ready to go. So we have m, okay, 0.25. We know what the starting point is in terms of the height here. And then we need to calculate a particular problem. So here's a question. Find the probability that the clerk spends between 4 and 5 minutes. Okay? Remember, this is the formula we're going to use to calculate an area in an exponential distribution. But this will only give you area to the left. Remember, we said m was 0.25. So the m here is 0.25. And we want to find the probability someone's between 4 and 5 minutes. So first off, I'm going to jump to the picture. I know I can draw this picture. I know what my m is. I know it's exponential, so I have this shape, and I want to be between 4 and 5 minutes. So this is the area I'm trying to find. That is not area to the left. That is area in between two values. And this formula will only help me calculate area to the left. So what I'm going to do is I'm going to find the area to the left of 5. So if I was to look at that, here's 5. I want to calculate the area all the way down here. And I can do that. Okay? So I want to find the probability that x is less than 5. All right, so if x is less than 5, 5 is the x in this formula, m is 0.25. So 1 minus e to the negative 0.25 times 5. Put that in my calculator. This is the answer I get. Okay, got to use that e to the x button on your calculator to do this, and you'll get 0.7135. But again, that's this area all the way to the left. That's not really what I wanted, but I'm going to use that. And then I have the probability that x is less than 4. Well, less than 4 would be, here's 4, and this is everything less than 4. Okay? So think about it. I got the probability to the left of 5, and I have probability to the left of 4. Okay? Here's 5, here's 4. I can get those things with this formula. Again, here 4 would be my x, m is still 0.25, so all I'm doing is switching out the 5 for the 4, plug it in my calculator, I get 0.6321. All right. But I really want to find the probability that x is between 4 and 5. So if I have, again, this bigger amount, I know how much that is, and this smaller amount, I know how much that is, and I want to find the amount in between. Well, if I take the bigger probability and I subtract the smaller probability, the probability that I'm less than 5 minus the probability that I'm less than 4 should give me the probability in between. And so the probability that the clerk spends between 4 and 5 minutes in this situation would end up being 0.0814. Much harder than a uniform distribution, right? Because we're not finding areas of rectangles. But we do have a basic formula we can use to help us find the area in an exponential distribution. It's a harder formula. I mean, you're going to need your calculator for sure to do the exponential function, but it's doable. Okay? The reason why I like doing that exponential example is not so much that we're going to use a lot of exponential distributions, is because it gives you the basis for how we're going to do the normal distribution, which is something we're going to do a lot of. So think of the same situation. Let's think about that post office clerk. But instead of them saying that the wait times were exponentially distributed, what if they said they were normally distributed? Well, that would change my picture. My picture wouldn't look like an exponential distribution like that, like we just drew, but it would be a Bell distribution like this. And so let's say I want to find the probability that I fit into a certain space here, that I'm less than some value, that I'm between two values, maybe there, or maybe I'm greater than some value, so here. You know, which area depends on the problem, but I want to find the probability. So I'll need to find these areas. What's this area? What's this area? What's this area? Well, we don't have a simple formula to do that anymore, right? Uniform distribution, very simple formula. Length times width, it's a rectangle. Exponential distribution, formula, not a very easy formula, but a formula to find the area to the left of some value. But when it comes to normal distribution, we're going to need a table or a computer or really a pretty advanced calculator to find the probability to the left of some value. And once we have the probability to the left, we can also find in between or to the right, you know, and we'll go through all those examples. But it's much harder here. And the primary way we're going to do it is with a probability table. And I'll give you the table that you're going to use. We have to practice using the table to get the answers that we need. Someone already used a computer to calculate a bunch of different values, and we just have to look those values up, okay? Because the formula is well beyond our scope of abilities in this course based off of the prerequisites. So here would just be a simple example. We're not really going to be able to do too much here yet, but I just wanted to give you an example of the normal distribution. So the final exam score in stats class are normally distributed with a mean of 63 and a standard deviation of 5. Keyword here is normally distributed. When we do these problems, they're going to have to tell you what the mean is and what the standard deviation is. Okay. Given the probability of scoring greater than a 65 on this test is 0.3446, find the probability the student scores less than a 65. All right. So they calculated this area for you already. They said the mean was 63. Something to note that we talked about with a normal distribution is that the mean is always right in the middle of a normal distribution. Okay, we talked about that. That's your mean. Okay, standard deviation will help us work with this distribution, and standard deviation, in this case, they just said was 5. I just write it off to the side. We'll need those things to calculate this area. Okay, but we're not there yet. So they did this area for you. They said that the probability that you're going to score more than a 65 in this normal distribution would be 0.3446. So given that, find the probability the student scores less than a 65. So less than 65 means you have to find this area. Okay? Can I use this area that I know to help me find this other area? And the answer is yes, because remember, one criteria for a probability distribution is that the total area in here, everything under this curve, if I was to add it all up, has to equal 1. So if I'm looking at this, and I'm cleaning this up, if I want to find this area, I know the total area is 1, and I know that this area is 0.3446, then I can simply find this area by doing 1 minus 0.3446. And I would come up with 0.6554. And so the probability that someone scores less than a 65 on this test is 0.6554. Probably someone scores more than 65, 0.3446. You could also change these to percentages. I could say 65.54% of the class scored less than a 65, and 34.46% of the class scored more than a 65. So now we're talking about how probabilities and percents are related to each other, just multiplied by 100. I could also ask the question the opposite way. I could have given you the probability that you were less than 65. I could have given you this probability, and you could have calculated this area, this probability. Same thing, 1 minus. Once you know one part, you can figure out the other part. But this is what we're going to need to do with normal distribution. And you notice it's not really that different than an exponential distribution, other than the curve is different, and how we calculate the first area that was given to us will be different. But once we have that value, we can do a lot of the same stuff. We're relating area and probability, and we can answer a lot of questions. Less than a given random variable, greater than a given random variable, between random variables. So then we're going to really have to study more on normal distribution. We're going to learn how to use the distribution table to calculate these areas, but we will get there.